Swayam Prabha. Digital India. Educated India.
Okay, let's start our next topic that is on smart sensors concept. Okay, so I'll tell you what it is and how it is very useful for many different sensors, and then we'll talk a little bit more on compliant mechanisms. It's a little bit of it analysis and things like that for mechatronic purpose. There's kind of mechanisms that we have seen in the CD-ROM drives and things like that. Okay, so let's begin with the concept here for the smart sensors. Let me get the pointer right. Okay, so you need to think about how we can make a sensor which can be smart in some sense, in the sense say it can self-calibrate itself, okay, or maybe it can have a range and resolution, tussle. Usually there is a tussle between the range and resolution. The sensors that can measure at a very large range, their resolution will be typically low. Sensor that can measure at a smaller kind of a range, their resolution can be high. Okay, so this tussle between resolution and range, okay, is always there. You cannot have something which is measuring very large kind of a quantity at very high resolution. I'll give you an example. You have seen, say we talk of a measurement of the weight. Okay, so if you go to the if you want to weigh gold, for example, you go to this goldsmith or jewelry manufacturer, and you give the jewelry to weigh. They'll have this small little microbalance which will give you very accurate kind of a weight of the jewelry that you are measuring. Now if you talk of other extreme, there are these weigh bridges. You might have seen in the what do you call your some kind of a there are these vendors who are having these weigh bridges which can weigh the cars, actually cars and trucks weight, they can measure. So you'll find the way you have these gas pumps or the petrol pumps, like that these weigh bridges will be there. If you ask them what is the accuracy of measurement of the weight, it will be in hundreds of if not tens of kgs. Okay, mostly hundreds of kgs. They weigh tons of material there. Okay, so there is a huge kind of a difference in the resolution of measurement, or the accuracy of measurement in on one side, if you go for very small kind of a sensor, very small kind of a range, like a gold measurement versus car measurement. Of course, one sees a need, whether there is a need for such a high accuracy. We don't need the car weight to be known to such a high accuracy. But the point here is that the things which are made to work with a larger range typically give you a lower resolution. Okay, and if you now demand though I want both little bit extend the range of measurement. Okay, say for example microbalance can go up to maybe 80-100 grams kind of a weight they can measure. But if you want to measure say up to 500 grams, okay, with the same resolution, or up to 1 kg with the same resolution, how can we make it possible? Okay, that is a kind of a question here. So think about it, like what kind of a thing comes to your mind to do that. Okay, so we'll talk and discuss a little bit more about this example. What kind of ideas that can be incorporated to enhance the range of so let's talk specifically about this weight measurement. Okay, so how the weight measurement principle is done. Okay, think about that and we'll come to that in a minute. So let's say you have to enhance the range of the sensor with this kind of a specific example of weight balance. Okay, so weight balance typically has a spring. Okay, you put some weight, this spring will deform and it will go down, and typically on the scale you will see some weight measurement done. This is one of the ways of measuring weights. Okay, other way you may have this kind of the balance that your subchi vendors they use, but right now we just focus about this kind of a system for weight measurement. Okay, so the markings here, okay, are typically say 1 mm marks, which we can identify from one to other. Maybe 1 mm we can identify. Now, if I want to weigh very small quantity or very small kind of a resolution kind of a measurement, then I use a spring which is a little low kind of flexibility. Okay, little low rigidity. Okay, highly flexible spring. So even for a small weight, it's going to get deformed, and I can see its marking on the weight scale here. Okay, now if I get this spring to go smaller in the stiffness or higher flexibility, then you see that from this point to this point, if the pointer can move, say this point being a limit, that spring gets kind of completely compressed here, and this is a starting point. So the range that you will be able to measure is proportional to the stiffness times the displacement. Okay, so that will be the range. So this is a whole displacement that can be possible for the spring, and then stiffness times that will be like a small range, because the stiffness is very small. Okay, if I increase the stiffness, then the range can be increased, but then what happens is still for a movement of 1 mm, I'll have to see that the larger weight needs to be put. So that means my resolution for this 1 mm kind of a measurement is going to be little lower for higher stiffnesses. Okay, so this is a point, can you all see this point? So now we are not right now worried about there is a friction that will also play some role, and all those kind of things are going to be there. Okay, so we are not right now kind of bothered about those things. Okay, so the question is then, how do you kind of make enhance this range of measurement even for a small resolution? I mean, even for a high resolution kind of or small stiffness kind of a scenario in this particular case. Okay, so let's talk about that now. So you appreciate this point that the sensitivity would decrease if we have a demand for higher range, or resolution will be low for higher range. Okay, and vice versa. So if you want to increase weight, then I propose that we put an actuator in this sensor. Okay, suppose we put an actuator in this sensor. Okay, so I formed little small feedback system around this sensor, such that the actuator is now giving an additional force. Okay, so I measure this on the scale. Okay, take its feedback to my actuator, and then actuate the actuator such that this reading always points to 0. So even if I put some weight there, like then like actuator will come in place. So look, the sequence will happen like that. Okay, I put a weight on this surface, then this pointer is going to kind of like go down. That means there is some error that is produced apart from away from the zero position, and then that error is fed back to the actuator, and actuator kind of gives some force and brings it back to zero. Okay, and this way, like you can always maintain like some small zero as a balance. Okay, it's called null balance. Okay, so you null balance the system always, no matter how much is the weight I'm putting. I mean, my system is always balanced. And now, depending upon what is the strength of your actuator, you can get now the higher forces possibility. Okay, so you can use a spring still like lower stiffness, but now the spring has no deformation at all because actuator is providing like the force to balance the weight. So that is a kind of a idea that is utilized here to enhance the range by using an actuator. Okay. So one can think of like what kind of actuator, how we can put it, and all those kind of things we are not right now worried about. Okay, but making sure that the actuator also doesn't have somehow any kind of additional friction force and things like that. Okay. So, can you see this idea? So with this idea, one can kind of like enhance the range of sensor and keep the resolution same, and you get some additional advantages. Just that any non-linearities that are existing in the system, they won't bother you here. Okay. Sorry about my mobile. Okay, so no non-linearities in the system, like say for example a spring, as you deform more and more, it might become non-linear. Okay, instead of like your scale is linear, but spring is behaving in some kind of a non-linear fashion because of the large deformations. Okay, to compensate for that, you would have like this marking also put in some kind of a non-linear way, but because we are doing this null balance with actuator here, we don't need to do that. Okay, you see this is a big advantage that you get. Okay, by doing this. So now one can think about okay, little bit more detail about this concept and say okay, oh look, if I'm doing this, okay, putting this actuator here, how do I know what is the actuator force I should apply? So that will come from some kind of a feedback control law, and one can think about what kind of feedback control law you can put here. Okay, so you have studied some like PD control, PD PID kind of controls or a proportional control. One can kind of employ that and say that okay, oh look, if I apply the actuator force proportional to the error, okay, with some kind of a gain constant, when slowly like it will go back to make the error zero. Okay, so that is how I can determine the actuator force. So you might have like some other kind of a ways. You just proportional algorithm may or may not give you great kind of advantage, or those kind of things can be discussed more. But the basic concept is essential to kind of capture here is that like I'll always maintain like a null balance or zero kind of a reading on the scale, and okay, then the question is okay, oh, look, I'm maintaining zero there, but how do I know how much is my weight that I'm putting on the surface? Oh, that can be there then calculated by just seeing like how much is the extra actuator force that you need to apply to maintain that balance. Okay, so when I put something on the weight balance, I'll have to apply some actuator force, which will happen through some kind of a feedback control strategy, and finally once it is settled in the final position, whatever is the value, that bias value that I need to apply, I'll get to know from that value what is the weight that I have put on the surface. Okay, so that is how one can get the actuator based on actual force, what is your weight that is put on the surface. Okay, now one can do some kind of a mathematics to do that okay, the actual force is say proportional KP kind of a control we can do. Then how do you analyze this system and things like that? One can do a lot of this kind of mathematical jugglery beyond this to find out, okay, what kind of proportional constant I should use, or do I need in addition some kind of a derivative also. Probably you'll need a derivative control also to kind of make sure your system settles into the final position rather than oscillating in the steady state. Okay, typically, like, that friction will be there in these kind of practical systems. So even if you don't put the derivative control in place, like, there will be a natural damping that will happen because of the friction in the system, and, like, your system will finally settle down. Okay, it's not going to continue oscillating forever. Okay, so you can kind of think of this mathematical model to represent, like, these dynamics of a system, and then, like, formulate, like, your control strategy and validate how your error behavior happens and things like that. Okay, so maybe you can try this exercise yourself and then, like, look at some of these developments that are given in the slide. Okay, so for any kind of a system, we'll come to this more in the detail when we start modeling different kinds of systems. But typically for modeling any system, say you have understood this system, actuator, there is some mass that will happen for this, the stage, that the dead weight of the stage itself, and then there is a stiffness, and then some kind of a the damping you can consider here, and then this becomes like a simple spring mass damper system, and for which, like, very well known equation, which is the force that I'm applying on the system will be mass times acceleration plus c times x dot, and plus k times x will be there in addition. Okay, so so this F that we talk here, like, this F is a force of actuator. Okay, that has to balance, like, finally, like, some kind of a dynamics of a system. Okay, I'm sorry to switch off these. Yeah. Okay, so the steady state value of the force, okay, will give you the final reading. Okay, so the expression, so these are the two expressions for the force. One is, like, based on the dynamics of the system, and other expression is what you would develop as a control strategy, okay, based on the feedback. So this the previous expression that you saw here was, we are considering that, okay, we'll apply the actuator force to be equal to this amount. Okay, so that was our feedback kind of in some sense for the system. So when xt is null balance or zero, then, like, you'll get this as a feedback expression for the force, and then, like, this is a system dynamics. Like, I think there's a term corresponding to the spring missing here. K times x also will be coming as a additional term here, but and then, like, we'll apply, like, some proportional control kp times x as this force. Okay, so that's how the things are going to happen. Okay, so right now the friction in the system is neglected. So when you do analysis of how this control would work, or, like, how this control will take care of or settle in the system into, then, like, you need to substitute this value of force from, like, as you are proposing as a control here in the expression of dynamics, and then do the analysis, and then, like, you'll be able to find out the details of how this force is going to, how this proportional feedback that you are proposing is going to affect your system, or affect your state x of the system, or you can, like, convert this state x into the error dynamics, and, like, study, like, what will happen to the error, how will it go to zero, will it go to zero instantaneously, or it will oscillate, how I can kind of have, like, the settling time of that oscillations controlled. All those kind of things one can talk about in lot more details. Okay, so we'll come to some more kind of analysis of such kind as we progress. Okay, you have done something already, but now we'll see from a little bit more practical perspective when the friction and other terms are there, or if you want to model the motor also, like the actuator also in the system in some way. Okay, how do you kind of take care of some of these things that will be seen here. Okay, so by the way, to balance this, if we use a screw kind of a system to drive, actuator means like the motor and the screw type kind of a system, then since it is not back drivable, that will not work here. Okay, so anything which is having a friction, a lot amount of friction will not work for such kind of a thing. So we will need to employ here a non-contact linear actuator which will kind of drive the system to kind of make things in zero. So you need to be aware about this. Like, okay, say we have seen, okay, oh, linear motion means like, no, we'll put some kind of a rack and pinion, or like, no, this screw kind of actuator. If you start putting that, it will for certainly balance, like, no, this through null balance. But now the kind of force that I need to apply is the system is locked in this place. Actually, any place you take, the system will be locked. So even if you now say, okay, if it is at 0 and I place some more weight on the system, since it is not back drivable, I'm not going to get any deformation up here. So the screw kind of actuators will not work here unless they are like, very smooth back drivability is there. Okay, so typically screw actuators will not have a back drivability. So here we need to have a non-friction, non-contact kind of a linear actuators to drive the system. Okay, then things are going to work here much better. Okay, so you can think about and like see whether you yourself are able to kind of do this error analysis here with one control expression or some other kind of a control expression, and like we can talk about that in more details later. Okay.